I think we are
Uh,
ready
all
to
right.
move to our next speaker. You already understand that John Donovan will be our next speaker. He is the former director of the microanalytical facility at the Center for Advanced Materials Characterization in Oregon at the University of Oregon. Also, he's the president of Probe Software, a company that publishes software for electron probe microanalysis. He has been active contributor in the field of microanalysis for more than 36 years. He's also an innovator, leader in the EPMA community. He has started his technical service at the University of California at Berkeley. Actually, I can read several pages about
No, no,
the
no,
of
no, no.
John.
That's good. That's good.
It's
That's
like
good.
a living history for the EPMA in general, I would say. So
I've
I
been
think
around.
we can introduce actually the title of his talk, which is about the correction of WDS and EDS secondary fluorescence artifacts from grain boundaries. And John, thank you so much again for your presence, and the floor is yours. Thank you so much.
Thank you. Thank you. Thank you for the invitation. So I'm going to talk about modeling and correction of secondary fluorescence from boundary phases. This is a problem I am seeing still to this day, especially in geology. I think the metallurgists have kind of figured out that they need to be aware of this because it can be worse in some of their cases. And here's a kind of a classic example of this. Let's see. Oh, there we go. So this is the example and this is not the worst case example in the periodic table, but it's a bad one. Castang actually talked about the worst one. But we have a sample of pure nickel, okay, and we have a sample of pure iron, and we're measuring nickel in pure iron, and we're measuring iron in pure nickel. So the boundary is right here in the middle. Sorry, I need to do the pointer. So here's our pure iron measuring nickel in that. Here's our pure nickel measuring, sorry, pure iron measuring nickel and pure nickel measuring iron. Here's our boundary right here. And this is the distance away from the boundary. And so what you're seeing here is that you get in some cases, in almost all cases, you have a continuum fluorescence that occurs. Um, and you're seeing here, we're seeing 1.6 weight% artifact. This is completely an artifact. It looks like a nice diffusion profile, doesn't it? But it's not. It's completely a fluorescence artifact. On this side here, where we're measuring iron K alpha and pure nickel, we're actually getting over 4 weight% of an artifact. So this is something that needs to be thought about. So as I would kind of, uh, you know, tell you, trace element analysis is difficult. It totally is doable, and you can get some amazing results, but don't believe everything you think. Um, and that means specifically to the geologists, please do not attempt to derive your thermodynamics from assuming it's diffusion when it's really a fluorescence artifact. Okay, so what's going on? So we have the important point is that you can have a beam incident material. Your electron beam comes in and the electrons are in an interaction volume, but the X-rays, including the characteristic X-rays, but also the continuum X-rays go in all directions, isotropically in all directions. If you happen to be near another phase, what we call the boundary phase, then you can get secondary fluorescence emitted from that material. And so this was, I think, one of the early papers on this was published a few years back, and this just has all the physics details on it. But I'm not going to get into the physics details too much. So, so here's an example of a paper. This was a very unfortunate situation where a presentation of one of our colleagues, a student of one of our colleagues, was giving a presentation at a lunar planetary conference, and they were analyzing olivines, lunar olivines, adjacent to some pyroxene and chromite materials. They're very complicated materials. And they presented this data here where they have an olivine phase here and this symplectite complex. And they were reporting, 2,700 ppm of chromium oxide going down to some base level they assumed. And they were saying this illustrates chemical zoning, potentially illustrates chemical zoning. And, you know, they stated that and what happened was the talk was given, a colleague of ours, Ed Vicenzi, pulled the student aside and said, I think you need to call John Donovan. And the student, to his credit, did call me. Unfortunately, the paper was already in press. So he couldn't really change the paper, but he had to add in a few sentences here and there because, as I will show you, what he showed was completely an artifact. And you can model this in CalcXAF, which is our free software. And of course, I'm sorry, but I switched the boundary and the chromite geometries here. So this is our boundary here. Here, it's this boundary here. But here we're going away in a negative X direction, but it's the same idea. And you can see that we're getting up to 4,000 ppm. And notice this is the elemental concentration here. And he was reporting oxide. And of course, if you look at the conversion, this number will be even larger. Now, this is not a pure chromite phase here. This is a mixture of pyroxenes and chromite, so it's not as large. But if you actually run the numbers, it's completely an artifact. So the entire thermodynamic basis of the paper was null and void. So, and relevant to that equation that Sergey showed, where the concentration of the standard is important for improving your trace element analyses. I just wanted to kind of give another example from the literature, and this is a paper that was done not too long ago, actually, 2017, and they did an analysis of nickel in some olivines, and they used San Carlos olivine as a primary nickel standard for some reason. I have no idea. This is ridiculous. First of all, the variance of the measurement in your primary standard is propagated to your unknown. Now, if the concentration is high in the primary standard, that variance is very small. And even worse is that the concentration of nickel in San Carlos olivine varies enormously. So depending on which San Carlos olivine you have, you could get a very different number, and that directly affects the accuracy. And the detection limit, as Sergey pointed out, is very dependent on the concentration. So you really want to use a pure nickel or a pure nickel oxide for measuring nickel in olivine, and that applies to all trace elements. Okay, yeah, there's the spread of data there. So let's go back. Let's go to first principles and think about this. Sergey used the same plot, and I'm going to use it again because it's a great plot. Here we have, as you can see, intensity on this axis, concentration here. We have a non-zero intensity for a zero concentration. There's our absorption curve. There's our fluorescence curve. And this is the important thing. When you're talking about major elements, and Annette mentioned about how the importance of a standard and the matrix correction when you're measuring these major elements. And I agree with her. A really good primary standard, and then a secondary standard that's similar to your unknown might be a great way to check things out. But these are multiplicative corrections. And so they have very little effect on trace elements. However, the background corrections are subtractive, and they don't have much of an effect on the major elements, but they have a big effect on the trace elements. And so here's what it boils down to. The major elements are, the dominant effects are your standard, the accuracy of the standard, the matrix corrections, the accuracy of the matrix corrections, your dead time correction, the accuracy of your dead time corrections, and of course, as discussed earlier, some ion migration effects that Chris talked about. So all these are very important for your major elements, but not so important for your trace elements. For trace elements, the dominant effects, which I'm going to talk about, are the background correction, a little bit. I'll talk about that. Interference is very little bit, but I'm mostly going to talk about the secondary fluorescence because I think this is the one remaining thing that people are really neglecting today. Okay, so that's what I'll talk about today. But let's just go over this real quick. So because it's a multiplicative effect, the error propagation in an absolute sense decreases as you go to smaller concentrations. If you have a 2% error at 100 weight percent, that yields a 2 weight percent absolute error. You might say that's not very good, right? Or you might say it's good enough. But a 2% relative accuracy at 100 ppm, that yields a 2 ppm error for a trace element. So that might be far lower than your precision. So it's really not that important. For the major elements, check the element accuracy using a maybe roughly matrix matched secondary standard from your primary standard to your secondary standard. For trace elements, you want to, you've got a very different situation. You've got the dominant effects again are background interference to secondary fluorescence, and this is a subtractive correction. So 100 ppm at 100 ppm error at 100 ppm, level, that's 100% error. That's terrible. But 100 ppm subtraction error at a major element at 100 weight percent, I mean, that's insignificant. It's just not important. So keep these things in mind. And of course, if the element concentrations are in between, then these effects are in between, but they're all scaled differently. So keep that in mind. Okay, and again, check your trace element accuracy with a zero blank. That is with a roughly matrix match. I'll get into the details of that in a minute, but okay, and we're going to talk about secondary fluorescence, but let me just wrap this up with the standard selection. For trace elements, for your primary standard, you want to use a high concentration of a synthetic mineral, hopefully, and pure element, pure oxide, whatever. Matrix correction doesn't matter. Statistics do. Check the accuracy of your trace element by using a secondary standard, that has a zero level of the element of interest. So check your accuracy of measuring titanium and quartz using a pure synthetic quartz, okay? Because if you know that the titanium level in the quartz is below the detection limit, you're going to be measuring zero. And we want to know how well we can measure zero, okay? When we're measuring major elements, we want to know how well we can measure the total, the analytical total. How close to 100 is it? But when you're measuring trace elements, you want to know how close you can get to zero. How accurate is your zero measurement? Yeah, dope standards are a waste of time in my book. So here's the example. I just said that. Okay, so just to remind people, a lot of these corrections, including the correction for secondary boundary fluorescence, needs to be included in not just in the matrix correction loop, but also in the correction loop for anything that's compositionally dependent. And the secondary boundary fluorescence correction very much depends on the composition of not only the beam incident phase, but also the boundary phase. So we're going to include it there. Okay, although if it's a very small amount of secondary fluorescence, you can just subtract it in an Excel spreadsheet. But if you're getting weight percent levels of boundary fluorescence, then you want to include it in the matrix correction. That's the critical point there. So for best practice, so I'll just reiterate, blah, 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 blah. Use a zero blank, and then check for your interferences and perform a quantitative interferences correction, and then model the fluorescence. If you're not sure, run the model. It only takes a very short time if you already have the materials calculated, and you can calculate for any X-ray and element X-ray and beam energy. Okay, so here's the interference correction. I'm just going to go over this really quickly. This is an example. I just like this example. We're measuring molybdenum in pyrite and in chalcopyrite, and we're getting a nominal concentration of molybdenum here, about 1.9 weight percent. This is in weight percent here. And the chalcopyrite, we're getting about 1.2. Okay, that's without the interference correction. Now, with the interference correction, we are going to see something very different. Now we see that the phases are statistically similar. The pyrite and the chalcopyrite both essentially are zero molybdenum. And look, what's this? Oh, now this is the molybdenum bearing phase. Okay, so that actually is the phase of interest. So you can read about that and published in '93, but we've updated some of these things since then. You can have complex backgrounds for trace elements. This can get nasty. So there's alternatives. You can not measure the background at all by using the mean atomic number method, which can be very, very useful, especially for low Z materials. And you can use the multi-point background method, which was developed for looking at very rare earth element rich materials. Okay, blank measurements. So then this is how well can you measure zero? This is kind of an important point. This is what we really want to know when we're measuring a trace element. And the classic example is the holes in the continuum that was first described by Norrish in, I think, 1990, yes. And these are artifacts of secondary Bragg diffraction. And you really need to think about these kind of things because these things can show up not just from a spectrometer artifact, but from a sample artifact. The gold M alpha line measurement in pyrite is a classic example of a sample absorption. So if you have, uh, uh, so by measuring zero, you can determine if there are problems either in your spectrometer, which is in this case is a secondary Bragg diffraction, or if it's in your sample. In the correction here, we can actually utilize a non-zero blank level material. In fact, the synthetic quartz that I have has 1.4 ppm of titanium in it, so I could actually specify that. But anything below 1 ppm is usually can be considered zero in the microprobe. So yeah, so we do that to improve things. All right, and that was the paper there. Okay, so here let's look at secondary boundary fluorescence now. All right, so here's a classic example of titanium and quartz. And as you can see, we've got quartz is our beam incident material. Here's our titanium, or rutile, whatever you want to call it. Our boundary is right here. This is our zero distance from the boundary. And you can see this is our K ratio. I think we're using TiO2 as our primary standard, and then these are the concentrations. The green is kind of the calculation of what we actually would see. Then the blue diamond is actually just only from the contribution from the boundary material. And the reason why they're the same here is because there's no titanium in the quartz example here. And you can get other kinds of things. Here's an example of looking at measuring calcium in a olivine adjacent to a northite, which is a calcium-bearing mineral. And again, this is not chemical diffusion. This is 1800 ppm, and it's completely an artifact. So this was described pretty recently in the Borisova paper, which I wrote with her and Paul Asamoah and some other people back in 19, because I went to an AGU conference and every diffusion profile I saw was a fluorescence artifact. And so I took Paul aside and I said, hey, Paul, there's a problem here. And he said, I knew there was an issue here, but I didn't realize it was that bad. Yeah, it can be that bad. So this needs to be looked at. There's a discussion on the forum that you can check out and lots of examples there. So how far could these boundary fluorescence effects go? Well, I was recently, well, some time ago now, contacted from Oak Ridge, and they were saying they're getting this weird thing where they're measuring zinc adjacent to some aluminum alloys at a considerable distance from the phase boundary, and they wondered what I thought about this. And so I modeled it, and so here we have pure aluminum adjacent to pure zinc, and we're getting about 1.4 weight percent at 1 micron from the boundary. And this is not electron leakage. This is actually X-ray fluorescence. The X-rays go much further than the electrons. And in this model, we don't even consider the electron leakage. Now, here's the interesting thing. You notice that here we only went out to 50 microns. Here I went up to 500 microns, so a half a millimeter away. And you see we haven't reached zero yet. In fact, this whole graph here is represented in this little box right here. So this continues, right? This is a log scale, clearly. What you can see is that we're still getting 20 parts per million at a half a millimeter from the boundary. And it's because, of course, zinc K alpha is a very penetrating X-ray. So you can be quite a distance away, and the continuum X-rays, and this is just continuum X-rays because aluminum can't fluoresce the zinc K edge. So just the aluminum continuum, just the continuum from aluminum is exciting that zinc a half a millimeter away from the boundary. So consider that. So also, you can actually get a negative boundary fluorescence artifact, okay? In this case here, we've got a nickel iron alloy. This is a NIST alloy. So we're measuring iron K alpha in this nickel iron alloy, and we're adjacent to pure nickel, okay? That's our boundary phase. And as we approach the boundary right here, you can see that our intensities actually decrease, okay? That's interesting, isn't it? In fact, it's about a 1.5% drop. But let me just take you through the steps to run this, because this is in the free CalcSAF software. It's actually in the standard app, but it comes with the CalcSAF software. So basically, you need to create some material. So here's your beam incident material, your boundary material, and your primary. There's about 200 or 300 compounds already calculated in the distribution. So when you download it, you get all the pure elements and a whole bunch of compounds, so you can start playing with it right away. But if you have another material you want to add, you can either add it to your standard database, or you can just type in a formula and it will calculate it. Each of these takes about 10 hours to calculate, so 30 hours for all three materials. But once they're calculated, then you can proceed to run the model, and it only takes a few seconds to run the model. And you can edit the kilovolts, the X-ray, the element and X-ray, and get the calculation. Okay, so this is an important distinction, because depending on whether the material, the analysis points are in a beam incident modeled material or the boundary modeled material, you need to specify that. So if your traverse goes across a grain boundary, you can't apply the same model to all the points. You have to look at only the points on one side of the boundary or another, because what's a beam incident material and what's a boundary material makes all the difference in the physics. So here, for example, is we're measuring iron in nickel adjacent to an iron nickel alloy, and you see we get a positive artifact about 1200 ppm at 1 micron from the boundary. And here we swap those. We're measuring iron still, but we're measuring now the iron in the iron nickel alloy adjacent to the nickel, and we get the negative artifact. So keep in your mind straight which is the beam incident material and which is the boundary material, because the physics will be completely different. Then there's a kind of an interesting, how am I doing on time, Ionis?
You do have around 20 minutes
Oh, okay, great.
before the time for questions. So
Okay, good.
20 minutes.
Okay. So there's a couple of aspects to this secondary boundary fluorescence correction. So the first thing is model it. Just run the model, see if you have a problem. If you don't have a problem, then you can just proceed as normal. But if you have a problem, at least you know you have a problem. And now, how do we want to deal with it? So this is kind of an important consideration, and I'll try to explain this. So depending on the orientation of your boundary to your WDS spectrometers, you can get a defocus effect or not get a defocus effect. If your Bragg crystal is kind of pointing at the boundary, I should say, if the boundary is parallel to your Bragg crystal, then you do get WDS defocusing. Okay, and that means that you don't get defocusing. Excuse me, abort reset. If you're in this orientation, then as you move in this direction, then there's no defocusing. But if you're looking at this crystal, okay, then you move away from that crystal that way, you are going to get defocusing effects. And Ben Busey published a really nice paper about this in 2018. So, and this can be, you can have two strategies. One is, I'm going to, not worry about the boundary fluorescence, effects, and I'm just going to do it like this, or I'm going to do it like this and try to minimize my defocus of my boundary, my fluorescence effects. The problem is that you have to be maybe 50 to 100 microns away before you really don't see a contribution from that boundary because of the Bragg defocusing. And I should mention that with EDS, you always see all of these secondary fluorescence artifacts because there is no defocusing on EDS. In fact, people used to call these system peaks because you would pick up X-rays from your sample holder, from the chamber, from whatever. So WDS is better in that respect, but it complicates the correction for this Bragg defocus because, as you'll see in a second. So here's an example. So here's a grain boundary measurement where we're measuring iron in quartz adjacent to pyrite. So the beam incident material is quartz and the boundary material is pyrite. And what's interesting and is important to think about is that as we move away from the boundary, okay, when we do the correction, we consider each point here to be the center of our analysis, because our beam is stationary, but our stage is moving the boundary away. Okay, so that boundary is actually moving away from us, and that's when the defocus effect comes into it. Uh, effect here. And so what we do is we want to measure a low magnification beam scan of a pure iron or pure iron oxide. And you can see that we've got a defocus effect here. So as we move, as the boundary moves away from the center point of our analysis, we actually see this defocus effect. And we can actually correct for that in the probe for EPMA software now. And here's an example of it. So we're going to measure iron on spectrometers 3 and 4, and this data is from Glenn Poiré at the University of Toronto. Thank you, Glenn, if you're watching. So here this is spectrometer 3, and you can see the Bragg defocus effects here, and here, by the way, is the uncorrected data, well, corrected and uncorrected data, and you can see that we have the uncorrected data is blue here, and the corrected data here, and you can notice that the Bragg correction is very small, it's minimal, because we're essentially moving in the same direction as the defocus, not perfectly, but roughly. And in fact, it's about a 20% correction, so it's a small correction. Okay, but spectrometer 4 is a little bit different. Here now is spectrometer 4, and we're now moving away from that. The boundary is moving away from our analysis point in the same direction, but it's about a 40% correction, and you can see that there's a larger Bragg defocus correction there. So. Okay, let's go over this again. First step, model the secondary fluorescence from the boundary phases in standard.exe, which comes with CalcSAF, free download. And then you'll see what you got. This example, the default example that comes up in the software is measuring cobalt K alpha in copper. And this was the example that Raymond Castang pointed out 60 years ago. He said, the microprobe is a great instrument. Well, he invented it. He says, but there is an issue. And so, and this is the issue, is that you can get 4.5 weight% of artifact at the boundary between copper and cobalt. So that's the first step, model it. Okay, we can model it now, thanks to the work by Xavier Levet and Cesc Salvat at the University of Barcelona. And then you have the option. If it's a problem, you can correct for it. If it's a tiny problem, you can just subtract it from your spreadsheet. If it's a larger concentration that's going to change the matrix effects, then you want to actually do it in the matrix iteration. And CalcSAF actually has a method where you can actually do that. You can actually load in an image, you can draw the boundary, and then you can analyze the points. It's a little cumbersome because you got to enter the data in an ASCII file, but it can be done if you're willing to do the work. And it's free. Now, in Probe for EPMA, it's a few mouse clicks. It's very, very easy. You open up the boundary correction window, you specify the boundary, here's your analysis points, and maybe if we have time, I think I could actually, do I have time, Ioannis, how are we doing?
Yes, more than 10 minutes, or less than 15, okay.
15, okay. I'm going to do this. I'm going to run standard, okay? And you open up the standard and it opens up a default database. This database that comes with the software by default is actually my standard database. But you can create your own standard database, and of course you can, if you close this, you can actually open a whole bunch of different databases. There's DHZ, there's Dana's, the American Mineral Crystal Structure Data Set, there's the ore minerals from Dana, there's the NIST database, there's a whole bunch of them, okay? But I'm just going to open the default one, because I know the numbers in it really well. And there's the PNETMA, the full Monte Carlo, the full Monty, as they say, I guess, Monte Carlo simulation. And then there's the kind of quick and easy modeling from the PenFloor, which is a variation on PNETMA. And it's a little simplistic, a little simplified in the sense that it always assumes a perfectly vertical boundary, and that's infinitely deep, and it doesn't assume any electron linkage, and there's some other things. But you basically just you specify, you browse for. So we could do something like, for instance, okay, let's do this. Let's say our beam incident material is titanium oxide rutile. So I'm going to go here, and here's all the compounds, right? There's a whole bunch of compounds here. And I think I already have TiO2 in here. Yes, I do. So you have it here, and then I'm going to specify it's next to a zircon. And I'm going to measure titanium. I'm sorry, I'm going to measure zircon. I'm going to look at the diffusion of zircon, L alpha, into titanium. And I'll just use the zircon as the primary standard also. And then you can specify the beam energy, and you just click generate. It's so easy. And it runs for a few seconds, and there you go. And so what you can see here, ignore the K ratio, but if you just look at the concentration, we've got about 800 ppm of artifact right here. 800. Oh, I have to, yeah, you can see my mouse. 800 ppm at the 1 micron from the boundary. And if we actually increase the energy, because we want to get good sensitivity, we want to really, zap the sample, it actually gets worse. It goes from 800 ppm, I think, to about 1,000 ppm. Let's see what it does here. Yeah, up to 1,000 ppm. So, model it. See what happens here. Okay, let's go back to here. So in this case, I made a synthetic iron nickel boundary. It's really tough to do this where you polish these things separately. So this is the pure iron, this is the pure nickel. I measured iron in pure nickel adjacent to iron. It's about a 30 micron gap here. We just couldn't get it any better than that. So the boundary is kind of somewhere in the middle there. And you can see without the secondary fluorescence correction, we're getting up to about 4,000 ppm. And with the secondary boundary fluorescence correction, we get 0 essentially. So this works. However, it's not that simple. We'd like to have it be this geometry, but sometimes it's going to be this geometry, or maybe it'll be a different geometry. In this case, we're actually going to get less secondary fluorescence than you'd expect from a given distance from the boundary, because it's not a vertical boundary. Okay, so we have less of the beam incident material and more of the, less of the boundary material and more of the beam incident material. So that's a problem. And how would we even measure this angle in our sample? I mean, it's like, you need to have a SIMS, depth profile. So, and then it's destructive. So you've lost it now. So just to point out in this particular example that Glenn did for me, this material here, I believe, is a very sloped interface, because if I actually apply the boundary right there where it looks like it appears, where it intersects the surface of the sample, we actually overcorrect enormously, okay? But if I move the boundary over to here, then it does a pretty good job. So we're actually running models right now, trying to see if we can come up with a geometric correction. Right now you can just move the boundary around until you get, you think you're getting a 0 where you're supposed to get 0, which I hate to do that. I hate to even mention it, but unfortunately, we can't be guaranteed to always have a vertical grain boundary. But anyway, just So I'm going to conclude that when we're measuring trace elements, we got to consider all these contributions to the trace element accuracy. Precision is easy to measure. We just do replicates. Accuracy is hard to determine. So first, use a high concentration primary standard. Check your 0 accuracy using a 0 blank. The two things we can be sure about in the world today is 100% and 0%. Okay, so 100% is the pure element or pure oxide, whatever you want to do. 0 is 0. If you have a material, especially a high purity synthetic material, and you know that there's nothing, or it's in the parts per million, or parts per billion, it's a 0 to the microprobe. The microprobe is going to see it's a 0. Can you measure that 0? Can you actually get a 0 when you try to measure a 0? Again, check for background artifacts. Annette mentioned this. Curved backgrounds, absorption edges, between your background and your on-peak position. Off-peak interferences. I mean, when you measure off-peaks, you have to make sure, you can avoid You can't avoid an on-peak interference, but you can avoid an off-peak interference by making sure you did a wave scan and check your backgrounds. And then check for on-peak interferences by check your X-ray tables and try to measure zero in standards that contain the interfering element but don't contain the interfered element. Do you get a zero there? Again, measuring zero is a really useful thing. And model your beam incident boundary material, see if there's a possible fluorescence correction, and if there is, correct for it. All right, thank you so much.
Okay, thank you so much again, John, for your excellent presentation. I really like it. And we have two questions up to now. One from Eva Del Hey. Thank you also for your presentation. She's currently working on diffusion profiles in olivines. So she said if you really need to do this correction in order to not misinterpret her data, can we use the software you demonstrate? Is it possible?
Yeah, so there's two softwares I showed. One is the CalcXAF standard package, which is free. Download it. You can run the models there and see how bad of a problem it is for you. And like I said, if you're willing to make the effort, you can actually perform the correction in the CalcXAF software. This is described step by step on our user forum. But if it's a small, 1,000 ppm, maybe even 5,000 ppm, it's not going to affect the matrix correction that much. And then you could just subtract it out in an Excel spreadsheet. So that's the easy thing to do. The Pro for EPMA software, it's a few mouse clicks, but it makes it very easy. You run the model and you use that same model that you ran to see if there's a problem to correct the problem, which is kind of cool. So you run the model, you get these results, and you can actually apply them to the data in Pro for EPMA or in CalcXAF if you're willing to make the effort. So yes, the answer is yes.
And another question from Harsal. Why is it important to deal with fluorescence corrections? That's the first one. And then, is it necessary that the two phases should be in disequilibrium, or if in equilibrium, for example, iron-magnesium exchange, how could the corrections performed, or any insights on that? So two different things.
Well, I think I said it in my talk. I mean, the reason why it's important is because you don't want to publish a paper like poor Stephen did, where he reported these diffusion coefficients, and they were completely an artifact. They were not real at all, and it's embarrassing. I mean, we don't want to be embarrassed. I mean, we're all human beings, and we don't like making mistakes. But when we make a mistake, we should admit it and we should correct it. And so the good news is that we can correct for it, because you don't know, depending. So, for example, in the example that Glenn chose, the pyrite in quartz and measuring iron in quartz adjacent to pyrite, he chose a very low temperature sample, hydrothermal sample. So we were very confident, even though it was a natural sample, we were pretty confident that there was no iron in the quartz. Now that might not be a great assumption, but it looks like it's a correct assumption. And so you want to so depending on the temperatures involved, you will get diffusion or not, but you're always going to get secondary boundary fluorescence in cases where the physics is produces it. So physics, you can't get around physics.
Yep, Annette, yes.
Just to add to that, specifically as a geologist, I mean, this is not just diffusion coefficients. We use trace and minor elements to calculate temperatures. We use thermobarometers, all that, and there is always a push because you want to have the last equilibrated pairs if you analyze mineral pairs. So everyone's always going as close to the grain boundary next to each other. And you want to make sure that you're not getting then data where what you're measuring is like you're getting a heating event or like you're tracking something that's not there because portion of the composition is really coming from the fluorescence. So also when you do experiments where you have very, very tiny grains, at times people test if their phases are in equilibrium. So not exactly the question that was asked, but sometimes you assess if something is in equilibrium based on their compositions. But if you have a secondary fluorescence problem, that would create a problem or would alter your conclusions. So every time you really rely on getting data from um, either grain boundary close to each other or tiny grains, or you try to assess if the inclusions in your sample record a different history than the large grains in the ground mass or something, you might run into that problem. And as John said, the first step in treating that is realizing that you have a problem, so that you can, even if you can't fix it, you can at least then approach your data with caution and see, like, okay, is that a Nature paper? Because you're showing something that no one has ever shown, or maybe there is a problem. An additional thing, which is a mix of comment or question, is I a good tip that I once got is so if you have like geometrics problems or questions with like, where is my spectrometer relative to your sample, and you kind of want to test that, or you want to test like, does my correction work? Of course, the problem is we can't change the orientation of the spectrometer. Sometimes you're lucky, you have the same crystal in opposite directions, so you can see how the data corresponds. But what we can do is we can put the sample in the other way around. We don't have rotation stages, but sometimes if you want to double check something, like, is that an artifact or not, or is my slope grain boundary versus bractive focusing going on? Take your sample out, rotate it if it's a thin section, the other way around, see if you get the same data within the statistics that you should calculate. So that can be another good test, that if you don't have the software, if you just or want to make sure that you're now correcting something proper. Yeah.
Yeah, there's two effects here.
Yeah.
There's the effect that's close to the boundary, where if the boundary is not vertical, if it's tipped this way or that way, you can get more or less of the boundary fluorescence effect. And then there's the Bragg effect when you're at a greater distance from the boundary, which can kick in. And that's why Glenn and I, he measured the iron on two spectrometers that were essentially at 90 degrees to each other, because it gave a nice illustration of that. I will be posting about this inclined boundary effect in the coming weeks. We'll see how that all works out. Yeah.
Yeah.
I
So
see
those
Steve has
inclined
a question.
boundaries, sometimes
yes.
those inclined boundaries, you can see them in your backscatter image,
Mm-hmm.
right? So that can be good.
Maybe, I
Especially higher
guess,
phase.
if it's sloped
Yes, there's enough contrast.
into the low Z material or something like that, maybe, yeah.
Yeah,
If it's
yeah.
sloped away from it,
The other thing, yeah, maybe. But the other thing was just two really quick questions. So one is about the software. Has the modeling software been multi-threaded, so each distance increment could be a separate, independently and parallel computed thread? The other is, have people tried, I don't know how well it would work, and there's context loss issues potentially, but people have been going around with what is it, self-rag, I think. It uses some kind of electrodynamic process to basically separate all the crystals from each other.
Oh, yeah,
And
yeah,
then you
yeah.
could take a thin section, a grain mount, and then maybe you don't have the other phase next door. Has
People
anybody
Well,
tried that?
you can
people
use a fib. You can use a fib. Yeah, what Annette just
Yeah,
said.
yeah.
You can use a fib. In fact, this work was kind of instigated about 10, 15 years ago, when we had a student who was trying to analyze titanium in quartz, Marissa Acosta, who did a great job on it. And she was studying the thermodynamics of this because she wanted to know, like Annette mentioned, what temperature was this quartz formed at, by measuring the titanium content in it. And so, we knew about the secondary fluorescence problem, and just as kind of one of the solutions that she did was she just used a fib to carve out the grains, mounted them on a TEM grid, and put them in the microprobe. So we had a TEM mount in the microprobe. To answer your other question, Steve, so I actually realized I forgot to mention one thing, and that is that you don't in this PenFluor version of PenEPMA, you don't have to calculate each distance, because once you calculate the par files, the parameter files for a given material, then it calculates all these points in seconds, and it does assume a point source for fluorescence, which is not super accurate when you're really close to the boundary, but if you get more than 5-10 microns away, it's pretty damn accurate. And so you can get all these things within in a few seconds. So no, you don't. I mean, if you're running the original PenEPMA software, yes, you have to calculate each distance from the K ratios of each, the intensities from each point from the boundary. But with this, am I still sharing my screen?
Nope.
Nope. Okay, that's the
Oh, but
problem.
you can share it if you want.
Okay, thanks.
Yep.
Yeah. So here, when you run the calculation, all these points, all these distances are calculated all at once, and it's because it's using a simplified model for calculating fluorescence, but it's pretty darn accurate. I mean, you can see we did that iron nickel vertical boundary, and it works, So the Bragg correction is a correction on top of that, and this inclined boundary is going to be maybe another correction on top of that. But the most important thing is just to run the model to begin with. Does anyone have a beam incident and boundary phase that you want me to run real quick right here, that just to see what happens? Any suggestions from anybody?
And just also to say, calculating these PenEPMA material files takes a moment, but that is threaded, and so you can open multiple instances and run these
Yeah,
over
that's correct.
something.
Yes.
And so we use that for nickel sulfide, nickel olivine kind of corrections, where again you have like a couple where one is like very, very high, where one element is a major element in the one phase and one in the other ones, and so you can also put in your actual mineral compositions as a material file. So it's
Yes.
what currently is yeah, I mean, those are based on standards or other materials. So you might be a material file for forstride and fayalite, but what you're trying to look at is maybe FO75 or something.
Yeah. So
you can produce that.
in the list of standards that comes with the software, there's all the Smithsonian compositions, so you can do your olivine or your obsidian. I think there was a good obsidian example here. I'm trying to remember what it was. Yeah, obsidian, you can put in an obsidian material. So if we look at calcium, whoops, I clicked the wrong button, sorry. If we look at say calcium in obsidian, let's see. Well, yeah, here's an obsidian, and then we look at it adjacent to a calcium-bearing phase, which could be a northite, and we're just using a northite as our primary standard. You have to have a primary standard, the one you're actually going to use. I mean, because the correction that we're doing in CalcSAF and ProFibMA is we actually adjust the K ratio during the matrix iteration based on the K ratios from the calculation. But if you're going to do the calculation in Excel, you just take the concentrations and subtract them out. You won't get a matrix correction adjustment, but at least you'll get a fairly good correction. So if I do calcium, and I'll leave it 20 kilovolts just for fun, and I run this here, and then there's an Excel output right here. You can actually output it to Excel right right there, as you can see.
Oh, and yeah, an important point is
okay.
you can
Oh, this
explore.
one has so. Oh, sorry. Go ahead. Go ahead.
No, I just want to point out for people that do these calculations, you can also play around with the accelerating voltage using
Yes.
that. And so
Yeah,
sometimes
right here.
drop it a little bit. You know, you go from 15 kV to 13 kV or something, and it might you might get into a spatial range then with this where you don't have that problem anymore.
Right.
So again,
It's
modeling.
It's possible. Yeah.
Yeah.
So that particular obsidian has a lot of calcium in it. So it's not a problem. As you can see, I had to go to log scale to actually see the effect. I think this obsidian has less calcium in it. Is that correct? Can't remember now. I don't have these all memorized. Nah, yeah, there is an effect, but there's a lot of calcium in this material, so it's a smaller effect. But but like I think I showed this before. If I just take a
Yeah, take the
here, I'll take the I'll just take the magnesium silicate, and then I'll just run it. So this is looking at calcium in magnesium in an olivine adjacent to a feldspar that has calcium. And if I turn off the log scale, you can see that we're getting about 600 ppm of concentration at the boundary. So, these things are worth knowing about. And yeah.
And you stated it, but it's true also for EDS. Like it doesn't matter what detector you're looking.
Yes.
It's X-ray physics.
Yes, it's just X-ray physics. Yeah. Yeah. There is a question here about the Joule software, and no, the Joule software doesn't have it.
Maybe I don't know if John or even Sergey wants to answer this question about the Joule software and whether any option is available.
Yeah, no, the answer is no.
Fluorescence.
Yeah, no, it doesn't have it. No.
Okay.
No.
Can we run the correction of the boundary between a mineral and matrix glass instead of a boundary between two minerals?
Say again?
If we can run the same correction at the boundary between a mineral and a glass.
It doesn't matter what
it doesn't matter.
It's the elements that matter.
Yeah, it's glass. Yes, glass is fine. I just did an obsidian example, I mean, so yeah, it works just fine. The only reason the obsidian example didn't show up so well is because there was a whole bunch of calcium in the obsidian, so it was swamped by the actual calcium measurement in the obsidian. Here, I can show you that effect here. So if I go back to this obsidian, and then I just run it again. And so, you can see the effect here. I mean, this much. So this is the amount that's actually in the material, and this is the amount that is from the boundary only. So it is visible. I mean, you are getting about 1,000 ppm, but it's just not huge in the overall scheme of things. But yeah, no, it can work with glasses, minerals, alloys, pure elements. Like I said, the one that was really amazing was the zinc aluminum one, and that was just wild. So if I go here and look at the beam incident material is pure aluminum, and it's adjacent to pure zinc, all the way down to Z. And we'll just use zinc as our standard. And then we'll look at zinc and we'll measure it. So in this case, and that's right, you might be able to find a situation where it doesn't have much of an effect, and I'll demonstrate that for you. So here we're getting about a 1.3 weight% effect. But if I switch to the zinc L line, okay, so I'm going to go, this is for the K line, zinc K alpha. Oh, yeah, zinc K alpha in aluminum, adjacent to zinc, and I change it to L alpha, and now let's run it with the L alpha line. And you see it's much, much, much smaller. It's basically 1,000 ppm instead of 10,000 ppm. So you can mitigate it to some extent, yes, by choosing different conditions. All right. Thank you, everybody.